Welcome to video 8.1 over the kinetic molecular theory. In this video, you're going to begin to understand the concepts of kinetic molecular theory and how it explains the movement of particles on all levels. This video is also going to help you be able to tell the difference between solid, liquid, and gases on a molecular level. As we get started, you need to see that there are tons of vocabulary terms. So as I go through these, make sure you pay attention and start checking out Quizlet to get these committed to your memory so that you can really begin to understand the concepts in this small but yet vocab heavy unit. So as we get started, I want you to envision a world or a scenario where millions of bouncy balls are dropped through the streets of San Francisco. What would that look like? What would be the random, chaotic but yet beautiful motion of those balls? Because when we try to think about the kinetic molecular theory, when we try to think about the movement of molecules, specifically when they're in gas form, this is what it's like. If our eyes were powerful enough, we could see all these molecules bouncing around our face at all these different times, going off the wall, off the clock, off our shoes, off our glasses. This is kind of what it would look like. And this is the heart of kinetic molecular theory, that in molecules around us, these balls or molecules will bounce like this forever and ever and ever. So as we talk about the kinetic molecular theory, I want you to envision this video of the randomness, the chaotic movement of molecules that are a lot like bouncy balls that are bouncing around and never stopping. So what we see here now is the kinetic molecular theory, which means, again, kinetic is movement, molecular means how molecules are moving, and the theory is what we believe to be true. So kind of like what you just saw on that video, on a molecular level, we believe all particles are in constant motion. And we're going to look at this concept of the KMT, the kinetic molecular theory. It's going to have 5 assumptions, and we're going to go more into how we would describe and explain that constant motion. So the other main idea here is that in different states of matter, the motion is going to vary slightly. And so what we see in the movement of gas particles will be slightly different than the movement of liquid particles will be slightly different of that of solid particles. In gases, we believe these particles are very free. They're bouncing very crazy-like, and they're continuously moving around off each other. In a liquid, we believe that those molecules still have the same amount of movement, however, they are confined to a certain space. So there's still freedom of movement here. That's why we see current and flow, and we see things mix by themselves within water, because there's still a random chaotic movement of those molecules. And then in a solid, we believe these guys are still moving, but their moving now is restricted to a vibration in place. And so ideally, or primarily, we're going to be dealing with things that are in gas form. And that's what the kinetic molecular theory really deals with, is things when they are behaving as a gas. And there are 2 scenarios here. We can have what's called an ideal gas, or we can have a real gas. An ideal gas is this idea that a gas is behaving in all 5 ways that make the kinetic molecular theory true. And a real gas is what we see in real life when certain gases do not follow the 5 assumptions of the kinetic molecular theory. And so you'll become more familiar with this as we talk about KMT here in a second. But again, understand there's this ideal gas concept versus a real gas. Ideal gas, they behave perfectly, they behave ideally, they behave in a way that fits all our 5 assumptions about our theory. And a real gas is when they don't obey all 5 assumptions of the kinetic molecular theory, and they behave more like what we see in real life under some situations. And again, you're going to see real gases behave real gases because of the intermolecular forces. So our first assumption of the kinetic molecular theory, or KMT, is that gases are made up of particles that are very, very far apart compared to their size. They're spread out. They have low density. If you had a glass of water sitting on your countertop, that glass of water, although it might be 10 ounces, when it evaporates, will actually occupy 1,000 times the size of that solid, of that volume. So that means one entire glass of water, when it evaporates, will actually go and fill up a giant room, because that's how much these molecules will spread out when they go from liquid to gas. So that's the first assumption of the kinetic molecular theory. The second assumption is that collisions are elastic. Collisions between gas particles are 100% elastic. Think back to that video I just showed you about the bouncy balls. Eventually, those balls are going to stop. Eventually, they're going to come to a rest, and they're just going to sit in the gutter somewhere for some poor sap to go pick them up. That's because their collisions are not elastic. They're inelastic. So an elastic collision is the idea that a bouncy ball will bounce forever, that no energy is lost on collision. And this is what we believe to be true about gas particles. That way, right now, around your face, constantly moving are all these small bouncy ball-like particles that are bouncing off the walls, and they're going to keep going on forever and ever. And so, again, this is something we believe to be true, and that when ideal gases behave ideally, these particles will never stop. However, in real gases, sometimes they do lose energy. Sometimes they lose energy because when they collide, their intermolecular forces take over, or because they're moving so slow compared to their density, they will begin to stop. Think about if you drop a bouncy ball versus if you drop a bowling ball. A bowling ball will bounce once or twice and then stop. A bouncy ball can bounce at least 10 to 15 times before it stops. And that's the difference between an elastic collision and an inelastic collision. But we believe in the KMT that gas particles will bounce on forever. Third is that gas particles are in continuous, rapid, and random motion. This is the idea of kinetic energy, or the movement energy. So we believe that right now, around our face, all the time, these gas particles are bouncing off each other, they're bouncing off the walls, they're bouncing off your glasses, and they're happening rapid and randomly, and they're not stopping. The fourth assumption is that there are no forces of attraction between the gas particles, or in other words, there is no intermolecular forces happening right here. The way we can overcome intermolecular forces is by increasing the energy, thus making these guys move faster and faster and faster, because the faster these particles move, the quicker they can bounce off each other and not give their intermolecular forces time to respond or to show up. So again, this isn't true in real gases. Real gases, they do have intermolecular forces, and this does play a large role in their behavior. So if we want something to behave ideally, we really have to heat it up or even remove the pressure of the environment so that they can behave ideally. But again, fourth assumption is there is no attraction, there are no intermolecular forces. These guys are free to bounce as they wish. And then the fifth assumption, which is actually a huge key idea here, is that temperature is not a measurement of heat, but temperature is actually the measurement of the average kinetic energy. This is a huge idea here. When you look at the temperature of a room, you're not really measuring the heat. You're not really measuring the thermal energy. What you're actually measuring is the movement, is the speed in which the particles are moving. This is pretty mind-blowing, actually. So what this means is that when we're at a low temperature, things stick together or the air is more still because at a low temperature, the intermolecular forces are taking over. So at a low temperature, we have low speeds, which then creates inelastic collision, which also allows the intermolecular forces to exist. At a high temperature, we're actually giving these guys energy to bounce off each other more freely, and their movement is much more random and rapid. And so again, high temperature, we have a high rate of collision, low temperature, low rate of collision. And again, depending if something's behaving ideally or real, will depend on how many collisions they're having. So those are the 5 assumptions. You might want to go back and review those sometime because that is a key major theme in what we're doing. So now we're just going to look at a few properties of gases, liquids, and solids based on the KMT, and then we'll wrap up the video. All right, so property of gases. First of all, no definite shape or no definite volume. We got that. Gases have fluidity. They can flow. We got that. We see jet streams in the air. We see how clouds move freely. Gases have low density. We got it. Because they're so low, we understand that we can compress gases. We can compress air very easily. We can compress a balloon if we would like. We could use the air compressor and put air back inside of a metal container. And so we see gases are compressible. Gases are able to diffuse and effuse. Diffusion is the idea of if I light a candle that smells nice, the people closest to that candle will smell it first, and the people furthest from the candle will smell it last. But eventually, that smell will fill up the whole room. So diffusion means particles start in one small area and spread out to the masses. Diffusion is the exact opposite. Diffusion is where smell or particles start at the masses and they come together through a small hole. Think of a vacuum cleaner. A vacuum cleaner can suck dirt in from all over, but it comes in through that small hole, and that's the process of diffusion. So again, gases have the ability to diffuse and effuse. Liquids, no definite shape, but does have a definite volume. Consider fluid. We see that. We see water current. We see how things will mix with themselves when you put Kool-Aid or food coloring in water. That flow, that fluidity, that randomness of particles will allow liquids to have fluidity or be fluid. They have a higher density than their gas counterparts. These cannot be compressed to our naked eye. Now, honestly, we could compress them a little bit if we had the right tools and technique, but to our naked eye, they cannot be compressed. We see liquids do have the ability to diffuse and effuse. So if I pour out a gallon of milk, the water or the milk is going to come from that small opening all over my kitchen table. At the same time, I can suck it up with a vacuum cleaner. I can take it back off the table and it can go through a small tube. I could use a straw and liquids are able to effuse. We see that they have surface tension. Again, this is because of the intermolecular forces are a little bit stronger at the surface, especially compared to the size of their molecules. And then also we see that they have this concept called capillary action. Here's a video of capillary action. Capillary action is when liquid is attracted to a solid. And so you can see the liquid here being attracted to the solid paper towel and eventually will allow these guys to move between that solid. Again, this is called the capillary action of how liquids are attracted to solids. And then finally, we have our solids. Solids have definite shape and volume. They do have movement, but that movement is in the shape of a vibration in a fixed position. They can't be compressed. Now, again, if we wanted to, we have enough machinery, we could compress things, but really they cannot be compressed in the way we're going to describe it in this class. They have a higher density than the liquids and gases. They cannot diffuse or fuse. They just sit there and vibrate back and forth. So, long story short, kinetic molecular theory. 5 assumptions that help us explain how solid, liquids, and gases behave on the molecular level. This KMT can help us explain and understand the different type of properties that solid, liquids, and gases have. I hope you have a fabulous day.
Like a hurricane.